we saw that with time reversal, you need to have, in a purely 2D structure, at least 4 Dirac nodes, and they're pinned at the time reversal invariant points. Right? The kx sigma x plus ky sigma y. You know, you can't have, or you can have kx sigma x plus ky sigma z, any of the sigmas, but you can't. You have to have 4 of them. So how about away from time reversal symmetric points? The reason why I'm going into this is because we're going to go into Weyls, which are stable away from time reversal invariant points. But first, let's understand 2 dimensions, and purely 2 dimensions, so no edge of anything, and ask, is there a Nielsen-Niomia theorem for Dirac nodes away from time reversal invariant points in 2 dimensions? Right? There's Dirac points at the time reversal invariant point, but away it's unclear. And we're just going to immediately realize that there's generically no way of having Dirac points away from time reversal invariant points. So this is a 2D Briand zone of a 2D model, not the edge of anything, a 2D model. So I have double degeneracy of bands here. All bands come doubly degenerate at these points. And I'm going to ask, can I have a Dirac node somewhere away from the time reversal invariant points? Somewhere at some momentum k. Okay? This is delta k. And I'm going to have delta kx sigma x plus delta ky sigma y. So at delta k is the difference between a degeneracy between 2 bands. The reason why I'm always looking at 2 bands is because I can always move things around. And with time reversal, I always need bands to come in pairs. But besides that, I can always just move things around and make and focus on just two bands. Unless I have a topological insulator where I need to focus on 4 bands. But anyways, so we're talking about 2D bulk. So this is not the 2D Briand zone of a 3D topological insulator. It's just 2D material. Every band has to have double degeneracy here. Can I have a double degeneracy point at some point k in the Briand zone? And the answer is no, because here I could immediately add a term m sigma z. Any term that's allowed by symmetry I can add. And this would not break time reversal, because time reversal only would tell me, so this flips under time reversal, right? Sigma is the spin, flips under time reversal. M doesn't flip, but the momentum flips also. So the only thing that this tells me is that the Hamiltonian around this k point is delta kx sigma x plus delta ky sigma y minus m sigma z. Okay? That's what this tells me. So if I have the mass at k equals to a mass at minus k, I can just add this term. Any perturbation that's allowed by symmetry is added. The bands of this would be m squared plus delta kx squared plus delta ky squared. Even though this was gapless and 2-fold degenerate, here I can just add a small perturbation and gap it. Okay? Nothing is stable with, right, in 2 dimensions away from time reversal invariant points. So in 2 dimensions, only at the time reversal invariant points is the Hamiltonian does the Hamiltonian have doublets? Okay, these doublets are just the Dirac point. So now I'm going to ask what symmetries, what if any symmetries do we need to add to a 2D Hamiltonian so that the Dirac points become stable. So we saw that without time reversal invariance, this can split, doublets can split. So now I'm going to ask, well, is there something more that I can add so that I can have doublets not split even far away? Well, the answer is usually yes. And graphene is the first example of that. But let's not go by example, but actually show how to think about it. In order to have something, so you have time reversal invariance. In order to have something not gap at some point, it doesn't help you if you have a symmetry, like time reversal, that brings you from here to here. All that it tells you is that the way this gaps at this point will be exactly the opposite the way this gaps at this other point, but you still can't gap it, right? The gap is m. So what you need is what's called in, well, what Moyes was calling little group. You need a symmetry of the Hamiltonian at this point, okay? If I have time reversal which brings it to another Hamiltonian, I'm just relating two different points in the Brillouin zone. I just need a symmetry at one point, bless you, okay? So, little group in K space is the set of symmetries, little group at K, set of symmetries leaving K invariant. Okay? So now if I want to leave K invariant and K is any point in the lattice, what am I left with? And I have time reversal. So time reversal moves me from here to here. What else do I need to add? Which one? Not inversion? Why not? Okay. Okay, so I need to add inversion. Inversion times time reversal. Time reversal moves me here, inversion moves me back. What other symmetries I can add? Rotation by? By how much? By pi. So that's C2z times time reversal. Okay? Does rotation and inversion differ if I have a 2D system? They don't differ if I don't have spin-orbit coupling. If I have spin-orbit coupling, if I have a spin 1/2 system, they differ. And this is a very important thing. This is why graphene, when you've got spin-orbit coupling gaps, if you don't have spin-orbit coupling, if you don't consider spin have spin-orbit coupling, as was shown by previous speakers, you can think of the system as spinless. You can make a rotation in spin space and make t squared from -1, you can make it equal to 1. The new transformation is time reversal times a pi/2 rotation of spin. Okay? So this one for spinless, okay, is equal to C2z. And what's the difference? Well, let's see. And this is very important when you're trying to build. So when you try to build representations and group theory of like materials. So for example, inversion squared is equal to what? What's the difference between inversion and rotation? Is there square? Inversion doesn't act on the spin. Okay? So inversion is always 1. C2z squared is 1 if spinless. But if it's spinful, it also rotates the spin by pi. C2 rotates the spin by pi. It's a transformation, it's a full rotation in orbital space, in spin space. So it's -1 for spinful. These have dramatically different consequences. The consequences are that this means that inversion times time reversal squared, time reversal does what with every spatial symmetry as a group element? So say I take a symmetry, say I take a site, I rotate it, and then I apply time reversal, or I first apply time reversal and then rotate the site. Time reversal is local, so it does what with any spatial symmetry, commutes. So that means that this is I squared T squared, 1 for spinless. Spinful, I mean spin 1/2, -1 for spinful. C2z times T squared is C2z squared T squared. 1 for spinless. What's for spinful? Huh? Come on. What is this for spinful? Okay. So they're the same. You can look at the group structure. So this is a group. I've just formed the elements of this group. Okay? Well, the whatever commutation relations of the group, the generator, etc. Time reversal commutes with everything. Okay? So you can see that they're very different for spinful. Okay? As a result, there's a result in band theory which tells you that if I have inversion and time reversal, bands always come doubly degenerate at every point in momentum space. So in other words, I can never have this at every point in momentum space because they are doubly degenerate, so they will come at every point in momentum space. And you can clearly see this. Why? Well, inversion is a unitary operator, U, 1. Time reversal is another unitary operator, U2. Times complex conjugation. It's an anti-unitary operator, time reversal. So this is it. So I'm going to call this some U times complex conjugation. Right? What is this U? Is this symmetric or anti-symmetric in the spinful case? Huh? Anti-symmetric. For spinful. Okay. So if it's anti-symmetric for spinful, what does it mean? And it leaves K invariant. That's very important. It leaves K invariant. So that means I can take the state psi at momentum K and the state inversion times time reversal times psi at momentum K. And so this commutes with the Hamiltonian. So this is an eigenstate. This is also an eigenstate at the same energy. So now I have two options. Either this one, IT times psi, is exactly psi or is different. If it's different, I have a twofold degeneracy. If it's the same, I have one-fold degeneracy. So is this the same or different? Different from the same proof. So always twofold, bands always are twofold degenerate. Okay? So bands stick together. So now degeneracy points between bands would have to be a fourfold degenerate point. If I have bands with inversion and time reversal, always for spinful system, always come in degenerate. So if I would have to have this, okay, I would have to have a fourfold degeneracy point here. Fourfold degeneracy points are very hard to get. Well, you can get them in 3 dimensions. In 2 dimensions, they're very hard to get. You can still get them in 2 dimensions, certainly not with this amount of symmetries. And the reason why they're hard to get, you can think of them as phase space. So for example, at this 4 degeneracy point, if the bands, if I could get this point, the Hamiltonian would have to be decomposed in 4x4 matrices. If this was a gap space, I could just project into this band, I'd get by with 2x2. That's the reason why I can get by here with 2x2, because I just have, I don't have 4 bands. But here, if there's a degenerate point and I'm trying to analyze it, my Hamiltonian will have to be made of 4x4 matrices. 4x4 matrices have, there's 15 of them, okay? To make a degeneracy point, I have to tune all the coefficients of the 15 matrices to 0. Not all of them, but a lot of them. There's 15 4x4 matrices. Okay, but out of these 15 4x4 matrices, as you go away from this point, there's only 5 of them, and these are the Drakh matrices. You remember in when you take quantum field theory, there's gamma 1, 2, 3, 4, 5. Okay, So I would have to take the coefficients of 5 of them to 0. That's a multi-critical point. So I could, by fine-tuning, I could do it, but it's certainly a accidental degeneracy, so it wouldn't be stable. Okay? So,
How do you get them in 3 dimensions?
well, in 3 dimensions, you don't get them just with inversion and time reversal. In 3 dimensions, you get them with inversion, time reversal, and C4. So inversion times time reversal makes inversion times reversal makes them doubly degenerate. But then C4 has 2 types of representations under inversion and time reversal. So you have a degenerate doublet by inversion and times time reversal in one of the C4 representations, another degenerate doublet in another C4 representation, and as they go on a high symmetry axis, they just cross. And being in different representations, they can't open a gap. But you need another symmetry. You wouldn't be able to get it, even in 3 dimensions, just with inversion and time reversal. Okay. Okay. Now, what we are going to do, however, is try to understand this in a much simpler. Okay, so basically, my point is inversion times time reversal keeps bands doubly degenerate. That's why in graphene, actually, graphene is gapped. There's a small gap by spin-orbit coupling, but this is twofold degenerate. Graphene is actually gapped. And it's topological insulator as a show, but it's, you can't keep the Dirac node. If you introduce spin-orbit coupling, you cannot keep the Dirac node stable. It always gaps. It gives you a topological insulator, but it always gaps. So I want to now show you how you can keep the Dirac node stable without spin-orbit coupling, just because I want to, we want to understand, well, we want to understand different things. So I know we're jumping between spinful, spinless, etc., but at least we're going to do things explicitly. So spinless graphene. For spinless graphene, inversion times time reversal squares to, for spinless, 1. Of course, when I talk about spinless graphene, if you want to talk about spin, you just double everything. Right? But it's a trivial doubling. If it squares to 1, this matrix U, if I say I times T is U times K, time reversal still has complex conjugation. This matrix U, is it anti-symmetric? Symmetric. If it's symmetric, can you say that psi is 0? You can't say anymore. Okay? So in the spinless case, bands with inversion and time reversal come singly degenerate. Of course, if you want to add spin, you just have to double them. One for spin up, one for spin down. But in any case, let's just talk about spinless graphene and understand what this gives to the system. So, whenever you want to think about like how a symmetry acts on the system, you can just, if you want, you can get it by brute force out of the orbitals of the system. You can just, get it by just, plugging in some unitaries for it, such that the group elements are such that the group commutations are satisfied. So I'm going to choose this U to be identity. Okay? Not a particularly good, actually, in graphene. I can't do this. In graphene, this is sigma x times identity. Okay? But I'm going to choose it to be identity, just to be complex conjugation, just because I want to. Okay? So, if I choose it to be complex conjugation, then I ran out of my other notes. Then the Hamiltonian H of k of graphene has to be equal to H what of k? H star, by implementing this symmetry. Agreed? So this makes a real Hamiltonian. And that's important for several things. the pz orbital band is going to transform neatly under this representation. And let me show you what. So let's revisit graphene. I'm going to revisit graphene. This is graphene. These are translation vectors, E1, E2. This is A and B. This is the reciprocal space of graphene. This is the so-called K point. It's not a time reversal invariant point. I can write these expressions exactly for these vectors. I can just give them, they're in the notes, if the notes are legible. And this K point. This K point has a symmetry group which involves C3. Okay, you can clearly see that it's C3 symmetric, but we'll get to that soon. All right? What I want to ask you now is, I want to do a little chemistry on graphene. So graphene has carbon atoms, which comes from have these configuration. 1s2, 2s2, 2p2. 6 electrons per carbon atom. Okay? I'm not going to worry about this guy because it's got too low of an energy. Yes? I've got my unit cell is made out of 2 sides, A and B, so I have 2 carbon atoms. Okay? So this is number of electrons. So I have 2s orbitals times spin, right? I have 2s orbitals. I'm not going to focus on this. I'm not going to focus on this. This is too low. It's always occupied. Think about it like this. Okay? Yeah? All right. Let's see. So this is 2s. Right. So this 2 is not the shell number. It's just because I have A and B per unit cell, right? I have 2s orbitals times spin, which is another 2. Agreed? But now I have p orbitals. So I have px, py, and pz. And I have px, py, and pz, px, y, z. 3 of them on A position, 3 of them on B position, times 2 spin. Okay? Which one do you think splits? I have pz orbitals, which are out of plane. Do in-plane orbitals, can they mix with, think of the graphene sheet that's actually standing graphene. Does it mix, do any orbitals mix with pz? Why? Huh? Yeah, so in group theory terms, you'd say that pz there's a mirror in plane symmetry. You can just, the plane of graphene is a symmetry plane. You just flip it. The pz orbital has odd eigenvalue under that mirror, right? Because it changes from pz to minus pz. S, px, and py have even eigenvalues. There's no way the pz band can ever, well, unless you buckle graphene and do all kinds of nonsense that we're not interested in, unless you buckle it or put a substrate, there's no way there's going to be any hopping between the pz orbitals and any other orbitals. The pz band is kind of inert. So how do they split? Px and py remain degenerate. Okay, so I'm just going to, this is 2s times 2 spin. I have px, I'm going to get a pz. They split down, and 2 pz from A and B times 2 spin, so 2 pz times 2 spin. And I'm going to get, 2 px, 2 py times 2 spin. Yeah? Agreed? Okay. Also from A and B positions. How many electrons have I got in my system per unit cell? Huh? 2 plus 2 times 2, 8. Times 2 A and B positions, 8. Okay, where would the Fermi level sit in this guy? I need to fill per unit cell 8 electrons. Where would it sit? 2 electrons times 2, 4 electrons fill up here. 2 electrons times 2, 4 electrons fill up here. To sit here. This would tell me graphene is an insulator. What's happened? Where am I wrong? So this is nonsense. So I should be wrong somewhere. Where am I wrong? Well, where I'm wrong is that these S and P orbitals, px, py, they hybridize. Those can actually, they have hoppings. And in graphene, unlike in bismuth, or like bismuthine, or like other things, in graphene, they're so close together, or the bonds are so strong, that they form a new set of orbitals, sp2. Okay? So the S and P, S, px, and py orbitals form in graphene sp2 orbitals. This band is inert. It doesn't couple with any of these. These form sp2 orbitals. There's 3 orbitals, right? And these guys bond. Okay? sp2 orbitals, how many of them there are there? What's an sp2 orbital? 3 of them. 1, 2, 3, right? And I can have bonding and anti-bonding sp2 orbitals. Okay? So 6 orbitals, which are the 4 p's plus the 2 s's, form sp2 anti-bonding times 2 spin. This is all the spin. Spin is just a nonsense quantum number here because I'm not looking at spin orbit coupling. 2pz, and here sp2 again times 2. Okay, bonding and anti-bonding. Now, where does my Fermi level sit? By spin. I need 8 electrons. By the way, these are electrons with spin, right, in carbon. When you go to the periodic table, you get all the electrons. Where does my Fermi level sit? So I have 6. I'm occupying all these. But I have 4 bands, 2 times 2 spin. I occupy them with 2 electrons, sits in the middle. That's why graphene is a semi-metal. Okay? Now, even if it sits in the middle, a gap could open. Okay? And a gap does open if I have spin-orbit coupling. But I'm looking at spinless systems. So, is graphene protected or not? So now that I know that my Fermi level sits in the pz orbitals, in the middle, see, this is not a matter of convention. This has to happen. If I have sp2 hybridization, and sp2 hybridization is the chemistry content of this problem. Everything else is group theory in graphene. The chemistry content is that chemists tell me that carbon atoms sp2 hybridize. If the S level of the carbon atom was much lower than the P level, it wouldn't sp2 hybridize. You'd have an insulator. If carbon somehow would have the S orbital much lower, sitting here, it wouldn't hybridize. You'd have your Fermi level sit here. Okay. So, even if it hybridizes, I could still, even if so the Fermi level sits in the pz orbital. So I'm just going to focus on the pz orbitals. And if I don't look at the out of plane, right? If I don't look at the out of plane, pz orbitals look like s orbitals. Just look down on them like this, right? Let's just call them s, so I don't say pz. They're obviously not s. They're pz orbitals. They sit out of plane. But for group theory, so I've told you, we've finished with chemistry. For group theory arguments, the pz orbitals look like s. So I'm just going to draw them as balls, like on this lattice. Okay. And I'm going to ask, why is graphene a semi-metal? Why does graphene has a gapless Dirac node? Especially at this K point. Okay? When I know that it could, potentially open a gap. So I need to find a reason what's happening at the K point. And most of the people, they write the nearest neighbor tie binding model. But of course, when you write the nearest neighbor tie binding model, the question arises, what do you do when you add more bands or more hoppings? More hoppings, nearest neighbor, next nearest neighbor, when you add a lot of stuff. So it doesn't matter. Graphene actually has no matter what hoppings you add, graphene will have a Dirac point here at the K point, and let's just prove it. So I'm not going to prove it completely. I'll give you this as an exercise, but it's proven in the notes. So what happens is that the K point in Briand zone, so this K point is not complex conjugation, right? You know, it's this point in the Briand zone. Okay? The K point in the Briand zone is invariant under several transformations. And this, you look at, this is called the little group of the K point. Little group of the K point has inversion times time reversal, right? Which is sends K into K. We just talked about it. It also has C3, right? You do a C3 rotation. Now, I am spinless, so what's C3? If I make the C3 rotation, what's C3 cubed? So what are the eigenvalues of C3? What are the possible eigenvalues of C3? 2 pi over 3, e to the minus I, 2 pi over 3, and 1. Now, if I have these two groups, what did I say this acts as? Let's call it this K, whatever. Too many Ks. So if bands at this point, if bands that come out of the S or PZ orbitals at this point have eigenvalues under C3, so C3 is a good symmetry group at K. It commutes with the Hamiltonian. I should be able to diagonalize both the Hamiltonian and C3. Yeah? So if the bands have eigenvalues under C3 at the K point, which are these rather than this, what does it mean? Huh? That they are degenerate. Is that clear? Yes? No? Should I go through it? So the point K in graphene, which is this point, not a time reversal invariant point. It's invariant under inversion times time reversal in C3. C3 has, I can diagonalize my block Hamiltonian at this point. Is going to have, the bands will have, the energy bands will have eigenvalues. The possible set of eigenvalues is these, because C3 cubed has to square to 1. Now, what I'm asking is, if I find out that the bands that come out of these PZ orbitals that I've already argued that are relevant at the Fermi level have these symmetries, have these eigenvalues, do they have to be degenerate or not? And the answer is because complex conjugation is also a symmetry of the Hamiltonian here. Complex conjugation tells me that this and this are the same energy. Okay, because complex conjugation relates this and this. So in other words, if I find a state psi such that C3 times psi is e to the I 2 pi over 3 times psi, this is an eigenstate of the Hamiltonian, psi. So H psi is equal to E psi at the K point. Okay? Then inversion times time reversal times psi is a new state psi 1. Okay? And there's two possibilities. Again, either psi 1 is the same thing as psi. Okay? This is a state of the same energy because the inversion times time reversal commutes with Hamiltonian. So either psi 1 is the same thing as psi or is different. But I'm going to compute its C3 eigenvalue, show you it's not the same eigenvalue, so it's got to be different. So let's see. So C3 times IT psi, first of all, you can see it from here. C3 commutes with inversion and time reversal, right? So that's IT C3 psi, which is IT times e to the I 2 pi over 3. This is a group element commutation. Now it's the eigenvalue. Time reversal is complex conjugate. So this is e to the minus I 2 pi over 3 IT psi. Okay? Clear?
So this is a general, can you make this into a general theorem, or is it only because you chose this particular form for the time reversal?
Now, this is a general theorem. It has nothing to do with choosing the particular form. Notice that I haven't actually used this form. Okay? I've said that IT commutes with C3. That's true no matter what unitary I choose. Okay? Inversion commutes with any spatial operation. Time reversal commutes with any spatial operation. This commutes with C3, no matter what unitaries you choose. Once I got it in this form, this is a number. So whatever unitary I choose here, I could choose U times K. It just goes through a number. General theorem. Make sense? Okay.
Is it general also regarding magnetic systems?
Now, you see time reversal.
Yes, of course, but let's say they have substituted some other symmetries.
So you can substitute. There's another symmetry that the graphene has that I haven't pointed out here because it's not necessary, that has got mirror symmetry along this line, so I can take this to this. That group is called C3V. It also has two-dimensional representations. Once you add magnetism, you're breaking both time reversal and this symmetry. So with magnetic systems, you have to be more careful. Generically is not true for magnetic systems because I did time reversal. Very good. Okay, any questions? So, just because of, okay, so I still haven't proved to you that these are the eigenvalues of the bands, right? I said that if these are the eigenvalues of the bands at this point, then they're a doubly adjoint. And what you can ask is, well, you told me that these look like s orbitals coming down. How can an s orbital have eigenvalue under rotation, which is 2 pi over 3, right? That's true if my unit cell was one site. But since it's two-site unit cell, what you are going to find out if you actually do it, and it's done here, is that if I take the C3 operation on the Fourier transform of the A-site creation operator, this gives you e to the minus I 2 pi over 3 CKA at the K point, at this K point. Sorry, at the corner zone. And CKB is equal to e to the I 2 pi over 3 CKB. This is done in gory detail in 3 pages of the notes, which I'll scan, and or like if there's somebody who's, somebody who doesn't want to go surfing, So just because, normally you would not be able to make an angular momentum. This is basically, it's got angular momentum. Out of s orbitals, if they're on site, you wouldn't be able to make it, but since they're off site, you find, or they're pz orbitals really, not s. But as I look down on them from this side, they look like s orbitals. Okay? So without any tight binding Hamiltonian or any low energy model, graphene has Dirac points stuck at the corner of the Brillouin zone, stabilized by C3 and inversion and time reversal. Okay, general out of the PZ orbitals. Okay, which we've established are the ones that are relevant to the Fermi level. Now you can do more things in graphene. You can actually.
Does this hold for all the lattices with C3 symmetry?
If you have no, so a very good point. So it holds for all the lattices with C3 symmetry and inversion and time reversal if you have PZ orbitals or S orbitals. What happens is that this representation 1 here does show up in sp2 orbitals. This sp2 orbitals, there's 3 of them, right? So you know if there's 3 of them that they can't, if it was just these 2 representations, you'd always have an even number of states at the K point. But these sp2 states have only 3, right? There's only 3 states. So the sp2 states, the way they do in the Brillouin zone, if this is the gamma point, this is the K point, they go like this.
Okay. Can I rephrase my question?
Oh.
If I do a generic tight binding model with, let's say, only next stable, so S orbitals, then this...
With S orbitals, yes.